Okay, when we're considering membrane potential, this following diagram might be helpful. What I've done here is I've just scattered sodium and potassium ions on the board. You can see they're evenly distributed. And then I've drawn a neuron plasma membrane to kind of indicate the fluid inside the neuron, what we would call the cytoplasm of the cell, versus this fluid outside of the cell, what's sometimes referred to as extracellular fluid. If we count the number of sodium ions in the cytoplasm of the cell, we can count 5 sodium ions. And if we count the number of sodium ions in the extracellular fluid, there are also 5 sodium ions. If we wanted to count potassium ions, we can count 5 potassium ions in the cytoplasm. And there's also 5 potassium ions in the extracellular fluid. So we've got an even distribution of potassium ions and sodium ions on either side of the membrane. This is not the case for typical neurons due to the fact that there is a sodium-potassium pump. So for reference, I'm going to put in red here a few of these sodium-potassium pumps along this neuron. And every sodium-potassium pump is going to work by taking sodium ions that happen to be in the cytoplasm and throwing 3 sodium ions out into this extracellular fluid, while at the same time grabbing any potassium ions out here in the extracellular fluid and throwing them back into the cell. It throws 2 potassium ions into the cytoplasm of the cell and 3 sodium ions to the outside. You can imagine, after not working for very long, throwing sodium ions to the outside and potassium ions to the inside, we're going to get rid of almost all of these sodium ions in the intracellular fluid, and we're going to fill it up with a bunch of these potassium ions. So letting this sodium-potassium pump work for just a little bit will change the landscape to look something like this, where we have removed most all of these sodium ions. There may be one left, and replaced it with many of these potassium ions. And conversely, the potassium ions from the extracellular fluid have been pulled to the inside of the cell and been removed from this extracellular fluid. There may be a few out there still, but there are going to be many more of these sodium ions that have been pulled from this cytoplasm and thrown to the outside. So these sodium-potassium pumps help maintain this imbalance of very high concentration of sodium ions in the extracellular fluid and very high concentrations of potassium ions in the cytoplasm. So that's half the story. That's how we get this change in charge of high potassium in the cytoplasm and high sodium in the extracellular fluid. The other part of that membrane potential was, how do these neurons maintain a slight negative charge in the cytoplasm? That's really due to the fact that if we look inside these neurons, they're going to have these negatively charged proteins. These are going to be called anions. Just big, large, negatively charged proteins. These are made by the cell. So they're built inside the cytoplasm, inside the walls of the cell, and they're too big to leave. So they can't make it out into this extracellular fluid. And the buildup of all of these negative charges inside the cell is what gives this cytoplasm a negative charge of about negative 70 millivolts. So this is where we start. Again, lots of sodium to the outside of the cell, very little potassium, and none of these negatively charged proteins. If we look inside the cell, there's very little sodium. There's lots of potassium ions and plenty of these negatively charged proteins. Again, that's how we get our resting membrane potential of negative 70 millivolts. Now, if these neurons are going to send signals, what we're going to see is there's going to be a rapid influx of sodium ions moving into the cell. That's going to be what we call depolarization. And the opposite of that is repolarization, where potassium ions are going to leave the cell. Just one side note, which we'll mention a couple of times and is handy to see here in this diagram. It's going to be easier for sodium to move into the cell. Sodium is a positively charged ion. It's attracted to all of these negatively charged anions. So when voltage-gated sodium channels open up, sodium very quickly comes in towards these negative charges. Compared to what we will talk about when we discuss repolarization, repolarization is going to have to do with potassium voltage-gated channels. These are specific to potassium ions, and they're going to allow these potassium ions to leave the cell kind of leaving behind this negatively charged proteins. Repolarization, or the purging of potassium ions, is not as easy as sodium ions moving into the cell. Again, sodium ions rushing in are going towards these negative charges. It likes negative charges, so it quickly moves towards them. Versus potassium ions that have to leave the cell, they too are positively charged ions. They like those negatively charged anions, so they're somewhat reluctant to leave. The only thing that really makes them leave is the concentration gradient, the fact that there's many of these potassium ions inside and very few of them outside. Let's graph this movement of ions moving into the cell versus out of the cell next. Okay, in this graph, we're going to graph what we would call an action potential. Let's define this action potential as a rapid change in charge of about 100 millivolts. Rapid, we're going to see that this is in the order of just a few milliseconds, and the change in charge is about 100 millivolts worth of a change in a charge. And we can graph that by doing a diagram that looks like this. On our x-axis, we're going to put time in milliseconds. So we've got 5 milliseconds on there, and our y-axis, let's put membrane potential. Membrane potential is measured in millivolts. And we'll start off by putting a measurement here of negative 55 millivolts. This measurement is typically known as threshold. We'll discuss threshold value. Neurons, like we'd mentioned just in our previous diagram, are normally at rest somewhere around negative 70 millivolts. We can graph this. I'll use a blue color to graph a neuron when it is at rest, negative 70 millivolts. We said this was resting membrane potential. So the neuron is not sending any signals at all. When the neuron does send a signal, we're going to see that from the resting membrane potential, it can really receive a signal that causes it to become more negatively charged. We'll describe this as an inhibitory signal. Or if it's an excitatory signal, it's going to cause the cell to become more positively charged. And maybe to think about what's going on here, just to maybe connect the previous drawing that we did to what we're graphing here, this membrane potential describes the change in the charge of the cytoplasm versus the extracellular fluid. And when the graph is down here at negative 70 millivolts, this, if we could peek inside the cell, let's take a cross section through that neuron. Again, we've got our extracellular fluid to the outside and our cytoplasm, that intracellular fluid, to the inside. At negative 70 millivolts, that is going to be a situation where the cytoplasm inside that cell is measured at a negative charge, negative 70 to be exact, and the extracellular fluid, the fluid outside of that cell, is going to have a slight positive charge to it. So negative charges to the inside, positive charges to the outside. What's going to happen as we go through this graph? A disturbance away from resting membrane potential and towards the threshold value means that positive charges are moving into the cytoplasm of the cell. I can graph that. We'll just use this different blue color to indicate that we've got a cell taking on positive charges. The cell is currently got cytoplasm that's negatively charged, but what's going on in this part of the graph is the cell is taking on positive charges towards the inside. Some of these positively charged sodium ions are moving into the cell and causing this cytoplasm to not be so negatively charged. It's drifting up closer to negative 55. Now, something special happens when we cross this negative 55 threshold value. It's going to set in place the motion of all of our voltage-gated channels. Let me just graph the rest of this real quick, and I'll add to this. Once we get above threshold, we're going to see the graph is going to very quickly make its way all the way up to about plus 30 millivolts. Let's make the top of this about plus 30 millivolts just to fill the rest of it out. We'll say negative 30 millivolts is about right there, and 0 is somewhere in between. And to really further describe what this is showing, if we are measuring somewhere up here at about 0 membrane potential, a cross-section through the cell at that point, if we look at that intracellular fluid compared to the extracellular fluid at 0 membrane potential, we would see that for every negative charge inside the cell, there is a positive charge. So those charges kind of wash out. Just like in the extracellular fluid, anywhere where there's a negative charge, there is also a corresponding positive charge. So there's no change in charge on either side of that membrane. We've got 0 membrane potential. When we go all the way up to the positive side of this chart, now it has flipped around where that intracellular fluid is now more positively charged inside compared to that extracellular fluid on the outside of the cell, which is now negatively charged. So this rapid change in charge, the cytoplasm goes from negatively charged, about negative 70 millivolts, up to plus 30, and then all the way back down to negative 70 millivolts we'll see in just a few milliseconds. So again, we leave resting membrane potential, and as the graph goes up, this is indicating that the cell is taking on more of these positive charges, and eventually the cytoplasm itself is going to be positively charged. This part of the graph is what we call depolarization. It is due to an influx of sodium ions. And how those sodium ions get in there are through voltage-gated sodium channels. I'll just say voltage-gated sodium ion channels. They're open, they allow sodium to move into the cell, and that's what's causing the cytoplasm of the cell to become more positively charged. Something happens at plus 30, which we will describe in a second, that prevents any more sodium from being able to move into the cell. Instead, what happens at about plus 30 millivolts is that instead of sodium moving into the cell, we're going to see that potassium ions are going to start to move out of the cell. So what's happening here is the cell is purging itself of those positive charges. It had a bunch of positive charges at the peak of this action potential, and in the part where we're going back down, this is what we would describe as repolarization. Repolarization is due to the loss of potassium ions. So we've got an efflux of potassium ions. They're moving out of the cell. And as the cell is purging itself of those positive charges, it's really just leaving behind those negatively charged proteins. This, again, is going to leave the cell more negatively charged and down here towards the bottom into this graph. Again, potassium ions are leaving the cell because during the repolarization phase, we're going to have these voltage-gated potassium ion channels that are open. I want to compare these two voltage-gated channels. One allows sodium ions to move through. The other one is specific only to potassium ions. But we're going to see that they operate slightly differently. The voltage-gated sodium channel is very quick to open. It's very quick to close compared to the voltage-gated potassium channel. This one is more like those apartment gates, if you've ever gone into an apartment complex where there's a gate that you got to punch in a code and the gate slowly opens up. You got to wait for a second. You know, once the gate starts to open up, you still got to wait a few seconds for it to open up wide enough that you can drive your car through it. And then once that gate starts to close, it actually starts to close, and sometimes people will still run through because they can fit their car through before the gate closes all the way. That's kind of like this potassium voltage gate. It's slow to open and it's slow to close like those apartment gates. We'll see that since it's slow to close, it is going to cause the charge of this cell to drop past negative 70 millivolts for a little bit of time. So as we go all the way down during this repolarization, we're going to see for a short period of time, these neurons are going to drop below resting membrane potential into a part of the graph that we're going to label as hyperpolarization, below negative 70 millivolts, and then it's going to slowly drift back up to negative 70 millivolts, our normal resting membrane potential. So there is our negative 70, our resting membrane potential. This part of the graph where we dropped below our normal resting membrane potential is what we call hyperpolarization. And what brought us to this hyperpolarization, like we said, was the fact that we lost too many potassium ions. There's once again an efflux of these potassium ions. Potassium ions are leaving the cell because during hyperpolarization, these potassium voltage gates are slow to close. So we lose a little bit of extra potassium ions. They leave the cell, leaving behind more negatively charged cytoplasm. So this could be, somewhere around negative 75 or negative 80 millivolts. And what takes us from this negative 75 or negative 80 millivolts and marches us right back up to negative 70 millivolts is the action of the sodium-potassium pump. Again, sodium-potassium pumps, they help maintain our resting membrane potential. If there are too many sodium ions inside the cell, the sodium-potassium pump will grab them and throw them outside. If there's too many potassium ions outside, they'll grab those and pull them back into the cell. So they maintain and set up this resting membrane potential of negative 70 millivolts. Okay, so we've at least labeled the phases of our action potential. Depolarization, the cell's taking on positive charges. Repolarization, the cell is getting rid of those positive charges. And in hyperpolarization, we drop below resting membrane potential. Here are some notable points that we want to point out on this graph. The first one is this threshold value of negative 55. This threshold value is basically going to be the trigger that sets into motion both of these voltage-gated channels. They both begin to open right here when we cross negative 55 millivolts. I said the sodium voltage gates are very quick to open. They open immediately and sodium rushes into the cell. We're going to see that this is also the time in which those potassium voltage gates are told to open. But like those apartment gates, they start to open, but it actually takes a few milliseconds before they're open wide enough that potassium ions can start to leave the cell. So there's a little bit of time, like we said, that it takes for those potassium gates to open. And then once we start to make our way back down this repolarization, there's another trigger right here at negative 70 millivolts, right here at our resting membrane potential. This trigger is the signal that tells both voltage-gated channels to reset, to go back to their original position. And what I want to show here, if I can just take a dotted line and go right through these trigger points that I'm referring to. In between these two trigger points is what we call the absolute refractory period. Absolute refractory period is a time at which your voltage-gated channels have been set to go in their series of stages. You're not going to be able to generate another action potential until these voltage-gated channels have reset back to their original position. We're going to see the trigger that causes these voltage-gated channels to open, like we said, is negative 55 millivolts, and the signal that causes them to reset back to their original position is negative 70 millivolts. Once we pass negative 70 millivolts, we enter this part of the graph where we are hyperpolarized. So before we actually hit our normal resting membrane potential, this part of the graph, if I can just put another dotted line between where we begin resting membrane potential and where we've crossed this negative 70 millivolt trigger, this portion of the graph is what we call the relative refractory period. Relative refractory period it's possible for these neurons to send another action potential. Again, we've crossed negative 70 millivolts. We've reset those voltage-gated channels, so they're all ready to go again. But we are entering this part of the graph where we're hyperpolarized, where we're even further away from this threshold value. That's the value that we need to cross to set these voltage-gated channels in motion again, to generate another one of these action potentials. Again, it's possible because we've reset those channels once we cross negative 70 millivolts, but we're further away from threshold. So it's going to take an even stronger stimulus to reach threshold than it would if we were just at resting membrane potential. We've come out of our relative refractory period. We're right back at negative 70 millivolts, and all we have to do is drift 15 millivolts in the positive direction to cross this threshold value. I keep mentioning this threshold value, and I said that we would compare graded potentials versus action potentials. And in this graph, now that we've graphed an action potential and this electric activity of a neuron, let me maybe add one more thing to this, which is the comparison between graded potentials and action potentials. We're going to say this a lot in unit number 4. But this part of the graph, before we cross threshold, again, once we cross threshold, we're going to be involving voltage-gated channels. But prior to that, everything down here in this part of the graph is going to involve chemically gated channels. And the strength of this signal could vary. This part of the graph is going to be where graded potentials exist. Graded potentials. These are just electrical signals that vary in strength. Sometimes they're not strong enough to reach threshold. Other times, like what we've drawn here, they are strong enough to reach threshold. They vary in strength. And the other thing that graded potentials have in common is that they operate by way of chemically gated channels. Chemically gated channels. Among one way of gated channels. But we're going to see graded potentials often involve chemically gated channels, and they vary in terms of their strength. Compared to the other part of the graph, let me use this orange color to trace this part of the graph that we call depolarization, as well as repolarization, and even this hyperpolarization. This whole part of the graph, until we get all the way back to resting membrane potential, everything in orange here is what we are referring to as an action potential. This action potential is our rapid change in charge of about 100 millivolts on the order of just a few milliseconds. It involves voltage-gated channels opening and closing very quickly. Again, graded potentials is before the threshold, but after we cross threshold, we've got voltage-gated channels that always open and close in the same amount of time. So the strength of the action potential is always the same versus these graded potentials, like we said, that vary in terms of how strong they are. This time, let's put the activity of our voltage-gated sodium channels in green. These voltage-gated sodium channels we're going to see have 3 different positions, and I'll just try and graph those here. To explain what I'm trying to diagram, what we have here is a plasma membrane. Let's label this as our plasma membrane. We're looking at a typical neuron, and these are the voltage-gated sodium channels. Just for reference, anything above this line is our extracellular fluid, and anything below this line is the cytoplasm, the fluid inside the cell. And we know at rest, this cytoplasm, this fluid is normally negative 70 millivolts. That's what we called our resting membrane potential. So all is fine, and in this first position, when neurons are at rest, when we're at negative 70 millivolts, the position of the sodium-gated channel is closed. In fact, one of the points here is we're going to see 3 different positions of this sodium voltage-gated channel. The first position that I'm about to label, we're going to see that this gate is going to be closed, but activated. meaning that it's closed, but it's capable of opening. And what happens here, if we look closely, there are going to be two gates on this channel. The first one, kind of facing the extracellular fluid, is what we call the activation gate. I'm going to put a little A with a circle around it, and a hinge that connects it to the other side here, kind of closing off this channel between the extracellular fluid and the intracellular fluid. There is going to be another gate to the inside that I'm going to label with an I. This is called the inactivation gate. So just for reference, the A means activation gate, and the I means inactivation gate. And you can see at rest, normal resting neurons, their voltage-gated sodium channels are closed. The activation gate is closed specifically. But what takes these voltage-gated sodium channels from their closed position to this position number 2 that we're going to describe as an open position? This open position, like we had seen in the previous graph, all we have to do is go from negative 70 millivolts to negative 55 millivolts. Once we cross this threshold of negative 55 millivolts, it's going to change a shape. It's going to cause a change in the shape of these voltage-gated channels. This activation gate is going to spring open very quickly. Remember, the inactivation gate is already open. So now this voltage-gated sodium channel moves very quickly to the open position. And we know once in the open position, there's an influx of sodium ions. We can say they move into the cell. So that happens very quickly. We graphed this all the way up until plus 30 millivolts. Remember when this cell had taken on enough of the sodium ions that the charge had moved to plus 30 millivolts. This is what we considered the peak of that action potential. And it caused a closing off of those voltage-gated channels. So once we hit the peak, what happens is this inactivation gate comes over here and closes off. The activation gate is actually still open, but the inactivation gate is what closes. And that's what I'm trying to point out here. This third position here is also closed, so no sodium ions can cross. But notice that there's a difference between closed and activated versus closed and inactive. This is a closed sodium channel that is not capable of sending another action potential. In order to send another action potential, these channels have to reset back to their original position. And what takes us from this closed and inactive position at the peak of the action potential and resets us right back to this first position, like we had just graphed, is when repolarization occurs and this cell repolarizes down past that negative 70 millivolt value. That resting membrane potential, we said, was the trigger to reset voltage gates. So now, once we cross past negative 70 millivolts, the positions change on these voltage gates. It's still closed, but now it's capable of opening. As long as we drift to threshold again, this thing is capable of opening and going through the whole motions again, letting sodium ions rush in, depolarizing until it hits that peak, at which point the inactivation gate closes off, and we have to wait to repolarize past negative 70 millivolts to reset this whole thing again. So 3 positions in this voltage-gated sodium channel. I'm going to add to this the potassium voltage-gated channel. I'm going to keep this on the board. I'm just going to use a different color and maybe the space down here at the bottom. The potassium channel is a little bit easier to draw because there's only 2 positions in this potassium voltage-gated channel. So let's label these voltage-gated potassium channels. Let's kind of paint the same scenario down here. I'm going to draw a line that represents my plasma membrane. And I'll have the 2 positions of the voltage-gated potassium channel. Once again, above this line is going to be our extracellular fluid outside the cell. Below the line is our cytoplasm of the neuron. This is our plasma membrane. And now when we look at the positions of these voltage-gated potassium channels, they've only got 2 positions. They've either got a closed position or we're going to see they have an open position. These are the ones that behave like the apartment complex gates. When they are in the closed position, I'm just going to draw this thing with a hinge indicating that it's in the closed position. And you'll remember from the previous graph that when we are in resting membrane potential, this negative 70 millivolts, when neurons are just at rest, both voltage-gated channels are closed. And the signal for both of these voltage-gated channels to spring open, like we said, is the same signal. It's when we cross this threshold value of negative 55 millivolts. Once this is crossed, that's the signal that tells these voltage-gated potassium channels to go from their closed position to the open position. But remember, it does this very slowly. So it's kind of slow to open. Once it's in this opened position, so now the gate has opened up, we're going to see what happens in the opened position is an efflux of potassium ions. They move out of the cell. So as the cell is purging itself of potassium ions, that's what allows this repolarization to occur. So this whole time potassium ions are leaving the cell, the cytoplasm has become more and more negatively charged. If it happens to drop all the way down to negative 70 millivolts, again, that is our signal to once again reset these voltage-gated channels. Resets those voltage gates. Again, we're right back to where we started, where once again this voltage-gated potassium channel is closed and is ready to send another action potential if threshold value is reached. One more thing to mention when we talk about this stuff, there are toxins, like a certain neurotoxin that you'll find in pit vipers that are capable of preventing neurons from sending signals. There are sometimes these proteins that you find in venoms or other types of poison that can sit here and block certain voltage-gated channels, and they prevent sodium ions from moving into or out of the cell. That type of disruption of neuron function can lead to body-wide, systematic failure. Another thing to mention too, sometimes there is issues with potassium ion levels in the extracellular fluid. In fact, one of the conditions that we will refer to at some point in the semester is hyperkalemia. Hyperkalemia is a situation where you have too many potassium ions in the extracellular fluid. Just to think about what that would cause real quick, normally for cells to repolarize, potassium ions have to move from the inside of the cell to the cytoplasm outside. And like I said before, the only thing that really allows potassium ions to leave the cell is the concentration gradient, the fact that there's a lot of potassium inside the cell and relatively little potassium ions outside the cell. So they leave the cell drifts down to negative 70 millivolts and resets these voltage-gated channels. Except in cases of hyperkalemia where there's too many potassium ions outside of the cell. If there are so many potassiums outside the cell that it makes it difficult for potassium ions to leave when these voltage-gated channels are open, what happens there is that cells fail to reach this negative 70 millivolts. And if voltage-gated channels can't reset, then instantly neurons fail to communicate with one another. And again, it leads to systematic body-wide failure. So it's going to be important to know how these voltage-gated channels behave and the triggers that cause them to open or to close.